kaanza tu.
Hello students and viewers, this is Eteta from Morogoro. My name is Fort MWAKITEGA, a mathematics teacher from 4. Last time we were discussing about area and perimeter, particularly on the area of quadrilaterals. Again, the lesson of today is about the same topic, but today we are going to discuss area for similar polygons. We are going to discuss in detail how the ratio of the areas of similar polygon is. Write as much together. Welcome so much to my lesson. As I said, we are going to discuss the area of similar polygons. This is our concern today. This is the lesson that we are going to discuss today. But before we discuss the area of the similar polygons, we must have the concept of similar polygons. What are the similar polygons? In Form 2, in the topic called Similarity and Concurrence, you discussed about similar figure there. We are again here discussing the same thing, which is similar polygons. Actually, similar polygons and similar figures are going to be the same. What differs is that for polygons, that means the figure must be a polygon, but for a figure, it can be any figure. So now we are discussing particularly the polygons. But we are saying that two or more polygons are said to be similar if and only if they have the same shape. If they have the same shape. To say that they have the same shape, for example, for those polygons they have angles and sides, we expect that the angles must be the same. So taking two figures or taking two polygons, we expect that for those two figures to be similar, the angles meant by those polygons must be equal. But again, we expect that the ratio of corresponding sides must be constant, must be also the same. If we take the ratio of corresponding sides side by side, then we find that the ratio is constant. Here we have two figures, this one and this one. Observing these figures, both are trapezium. This is the trapezium, but also this is the trapezium. Observing to this one, this side corresponds to this one. Again, this one corresponds to this one. This side corresponds to this side, while this side corresponds to this side. In this way, you can observe that even the way they look like, they are similar. They have the same shape. Therefore, these two trapezium are called similar polygons. Are called similar trapezium. On that case, you know the kind of polygon. But because we are discussing polygons, these are one of the similar polygons. Why so? Because they have the same shape. Observing the way this one is and this one, and again this one and this one, but also this one and this one, this one and this one, they are the same. Therefore, the two trapezium are similar figures. But as our concern, as we said, we are going to discuss the area of similar polygons. And our main concern on that, it will be the ratio of area of similar polygons. In order to work on that, in order to learn the ratio of areas of similar polygons, we can consider two triangles. For example, if we have triangle ABC and triangle A dash, B dash, and C dash, which are similar. Because we are going to discuss the area of similar polygons, so we must make sure that the triangles are similar. Now, for example, this one is the first triangle. And again, we should have the second triangle. By observing the way they are, they have the same shape. So these one are the similar polygons, similar triangles, just by looking. But we need to have some rules that guide us to confirm that whether they are similar or not. But by just looking, you can observe that these are similar. This one and this one, they are on the same way, but also this one and this one, they look in the similar way, and this one also, they look in the similar way. So as you can see, they have the same shape. It's not the issue that these are both triangles. No, we have to observe the way they are. You may have two triangles but with different shapes. For example, you may have isosceles and a right angle triangle. Those cannot be regarded as the similar triangles. Why so? Because they have different shapes. So for this one, they must have the same shape. And as I said, we have to use the concept of angles to confirm whether they are similar or not, and the other rules. As we say that the similar polygons must have the same angles, but also they must have the corresponding sides must have the same ratio. Now, our aim is, we said we are going to discuss the ratio of areas of the similar polygons, and we have these two triangles. Now let us name them. For example, call this A, and this one should be it should be A dash, since this one is the corresponding verses. And again, we should have here B, and the corresponding vertex it should be B dash in this way. And again, we should have vertex C, and the corresponding vertex should be C dash. So this one corresponds to this one, this one corresponds to this one, and this one corresponding to that one. And again, we want to name the size. We can name by observing the angles and the opposite to that angle. For example, if this is A, then the opposite to this A, the side which is opposed to this vertex A is this one. So let us name it A, using small a. And again, this is B, this vertex is B, therefore the corresponding, the opposite to this one, it will be B. Yes, this one corresponds to this one, therefore if we it is A, this one will be A dash. And again, as I said, this is B, therefore the one which is opposed to this one will be this one. Let us name it B. And again, the corresponding, it will be this one. They are both facing the same angle, equal angle, since we say this one and this one must be equal. And again, C, which is opposite to vertex C. Therefore, this also, we should have vertex C dash, which it will be opposite to vertex C dash. Then, these are the triangles which are similar. As we said, we have to discuss the ratio of areas of the similar polygons. Now let us move ahead again. The corresponding size, as we said, A and A dash, B and B dash, C and C dash. Those are the corresponding size. Therefore, even if we want to get the ratio of the corresponding size, we'll have to take A over A dash, since we are dealing with the corresponding size. C and C dash, B and B dash. As you remember, ratio is the same as dividing. So, if you want to get the ratio here, it is the same taking A over A dash, B over B dash, and C over C dash. And as we said, for the similar polygons, the ratio must be constant. So we expect that we are going to get the same answer. And that ratio, let us name it K. Let us use the K to denote the ratio for corresponding size. It will be A over A dash, B over B dash, C over B dash. All this one should be equal. Otherwise, the triangles will not be similar. Now, the area of triangle ABC, this one, the area of this triangle. We had different concepts on finding the area of the triangle. One is by using the formula which says half times base times height, provided you have the height. But in this triangle, we don't have the height unless you project it. But because we don't have, there is an alternative way to find the area of that triangle. And here we are saying that you can use the two sides, and for example here we said this one you should have and this one also you should have. So for example, if we consider that we have A and we have B, and now let us decide our angle that should be used, this should be C. This C, it will be the included angle. And we have the formula of finding the area of the triangle by using the included angle and the two sides. Therefore, it's going to be a half times the product of these two sides, which is AB, and times the sine of the included angle, which is angle C. So it will be this one, to be a half times A times B times sine C. Whilst we multiply by sine C, we say this C, it is the included angle which is formed by side A and side B. Therefore, the area of triangle ABC is going to be a half AB sine C. Similarly, the area of the another triangle, which is the triangle A dash B dash C dash. This one also we can use the corresponding angle to C, which is C dash. And if we decide to use this one, therefore we have also to use side A dash and B dash. Then again with this triangle, by using this one and this one and this one, therefore the area of triangle A dash B dash C dash is going to be a half times the product of these two sides, which is A dash and B dash, times the sine of angle C dash. So the area of triangle, this one to be this one. But you have to remember that we said for the similar polygons, the corresponding angles must be equal. And we said angle C, it corresponds to C dash. Therefore, we expect that sine C, it should be equal to sine C dash. Since C and C dash are corresponding angles, that must be equal for similar polygons, or for similar triangles in this case. Now, the ratio of the areas. The ratio of areas, as we say, the concept of the ratio, that means dividing. So we have to take the area of one end or of one triangle and we divide it by the area of the another triangle. Now, for example, if we decide to take the area of triangle ABC and divide it by area of triangle A dash, B dash, and C dash, then this one we have already discussed that the area of this one is to be a half AB sine of C, and the area of triangle A dash, B dash, C dash is going to be a half A dash, B dash sine of C dash. Now, since our concern is to find the ratio, then let us keep on this side, wait on this side. Here we say sine C and sine C dash are going to be equal. Also, because C and C dash must be equal, since we are dealing with the similar triangles. Therefore, this one and this one, they are going to be cancelled if we work on that. And again here, we have this half and also here half. Since we are dividing, they are also going to be cancelled. This one and this one will be cancelled. Therefore, it will be the same as A, B. On the numerator, we will have AB, but on the denominator, we will have A dash and B dash. Yes, this one can be separated in this way. You can take this one A over A dash times B over B dash. Yes, since it is possible. Here, this means that A times B, because multiplication, it has no effect even if you don't choose it, but provided you drop it or you use bracket. So because here we have only A, B with no operation, that means A and B are multiplied each other. Similar to this one, that means A is multiplying to A dash is multiplying to B dash. Therefore, it can be separated this way. And of course, the numerator, we know that they are multiplied by the numerator, and the denominator, they are multiplied by the denominator. So this one will be the same as A times B, and again, A dash times B dash. But if you remember, we said that A over A dash, it gives K. But also if we take B over B dash, we also get the same answer, which is K. Even if we take C over C dash, we get also the same value, which is K. So similar to this, you can observe that here we have A over A dash, and we said for this one to be the same as K. Similarly, B over B dash, we are going also to get K. Then it will be K times K, in which we get K square. Yes, we get K square. We get K square. Now, this one to be the what? It will be the ratio of the area between area of triangle ABC and the area of the triangle A dash, B dash, and C dash. That will be the ratio, K times K to be the ratio. Actually, if you take K times K, you get K squared. Yes. Now, if you remember, on the cases when we were discussing about the areas and areas of quadrilaterals, we have observed that all the formulas are derived by dividing the given polygons divided by a number of triangles. For example, we saw the case of parallelogram. You divide the parallelogram into two triangles. Similarly, for the square, you can divide into two triangles, or four, or whatever. Similarly, on the case of the rectangle, we also divided the rectangle into two triangles. Similarly, on the rhombus, we do the same. Therefore, any polygon can be divided into triangles, into a number of triangles. And here we have seen the way the ratio of the areas for the triangles, for the similar triangles. This one can be applied in the similar way to the other polygons. And we have said that for similar polygons, each polygons can be divided into triangles which are similar to the triangles formed in other polygons. For example, if we have maybe a rectangle, it can be divided into two triangles. Then, if we have another rectangle which is similar to the first triangle, to the first rectangle, we can divide the first rectangle into two triangles, and again the second rectangle into two triangles, and there the triangles which are formed from the first rectangle will be similar to the triangles which are formed in the second rectangle. And in that way, the ratio is going to be the same, since for the triangles that will be derived will give you K squared. The ratio to be K squared. So here we are saying that the ratio for the areas will be K squared. For n similar polygons, the ratio of the areas will be K squared. So generally, if the ratio of the lengths of the corresponding sides of two similar polygons is K, then the ratio of the areas will be K squared. Keep in mind that if the ratio of two similar, the ratio of corresponding sides of two similar polygons is K, therefore the ratio of the areas is going to be K squared. As we have discussed that the case of the triangles, we saw that the ratio for the corresponding sides of the triangle, it was K squared. Then the ratio for the areas, it was K squared. Therefore, if the ratio of the corresponding sides of two similar polygons is K, then the ratio of the areas, it will be k squared. Let us see the examples of how this knowledge or how this concept is applied in different portions. This is the first example on this particular lesson. The question says, given two triangles which are similar, the length of one side is 8 cm and the length of the corresponding side is 14 cm. If the area of the smaller triangle is 24 cm square, find the area of the other triangle. Yes, we are being told that there are two triangles, and we are given the one pair of corresponding sides. The side of the small triangle is 8 cm, while the side of the bigger triangle is 14 cm. And also we are given the area of the smaller triangle. What we have to do, let us see. The corresponding sides are, let's call S1, which stands for the side of the first triangle, which is 8 cm. And S2 should stand for the side of the second triangle, which is the bigger triangle, which is now 14 cm. Now the area of the smaller triangle is A1. Let's call it A1. And in that way, the area of the larger triangle, let's call it A2. But the ratio of the corresponding sides, since we are given the corresponding sides, what we have to do? We have to divide. So you have to take the smaller over the bigger. So we have to take the length of the side of the smaller over the side of the bigger. It's not a must, but if you decide to take a smaller to a bigger, it must work in the similar way even to the case of the areas. So in this way, if we take S1 over S2, it will be 8 over 14, since S1 is 8 while S2 is 14. Now, the ratio of the area. The ratio of the area, we know that it will be k squared. And working on this one, for example, if we simplify 8 over 14, we get 4 over 7. Squaring 4 over 7, we get 16 over 49. It will be 16 over 49. That one will be the ratio of the areas. Since the ratio of the size, it will be 4 over 7, therefore the ratio of the areas will be 16 over 49. Now we have to compare. Taking a 1 over A2, area 1 over A2, it should be equal to the ratio that we discussed, which it will be 16 over 49. Now here you can apply cross multiplication. Doing so, it will be this one and this one, you get 16 A2. And this one you get 49 times 24. Now because our aim is to find A2, which is the area of the bigger triangle, now you can make A2 the subject. We'll have to divide here by 16 both sides. And weight on this one will remain with the A2, and this side to be 49 times 24 over 16. Weight on this one, take a normal multiplication and division, you are going to get 73.5. So A2 it will be equal to 73.5. That one will be the area of the larger triangle. The area of the larger triangle. Yes. Again, let us have another example, which is the example number 2 on this lesson. And the example says calculate. We have 3 parts here. Part A it says AD, and part B says DC, and the C it says the area of the triangle ABC in the figure below. The figure we are given is this one. It is marked by A, B, C, and D here. But you are required to find AD, which is this one, the distance from here to up to here. And again, we have to find DC, which is from here up to here. And again, we have to find the area of triangle ADC. The area of triangle ADC. Yes, the way we discuss you have the first thing to know here is to know which concept you are going to use. Of course, with this concept, it can help us to find AD, DC, but also the area of triangle ADC. Since triangle ABC, we are given the dimensions. We are given the all sides. Now, our work will be to find AD, DC, and also the area of ADC. But as we discussed, I think you can try for your own, taking the ratios of the corresponding sides, so you work on part A, but also on part B. I'm going to deal much with part C. But on this one, I'll try to explain to you how, actually to show you the corresponding sides. And I know that because we are given some of, therefore it will be easy for you to find the other sides by using the concept of the corresponding sides and again the ratio of the corresponding sides. Let us match together on this exam. Here we must have, from the figure, we can observe two triangles. We can observe the first triangle, which is this one, triangle ABC. This one, the bigger triangle, which is ABC. This is the triangle. And again, we can observe another triangle, which is triangle ADC. This one on our figure is this one, ADC. This is also a triangle. But you have also to keep in mind that here at A there is 90 degrees, but also here at D there is 90 degrees. And again, you see it is formed in both triangles. It is formed by triangle ABC, but also it is formed by triangle ADC. That vertex is common. It is used to both triangles. The other issues that you must remember are these sides. Now, on these triangles, AC, it is 6 centimeter. Which is this one, it is 6 centimeter, and here it is 6 centimeter. And again, we have AB, which is 8 centimeter. On this one, we don't have that one. And again, BC is 10 centimeter. We are given there. We have been told that this angle, BAC, it is a right angle. This one is a right angle. It is a 90 degrees. And again, on this one, ADC, as I told you that we have also a right angle, which is also 90 degrees. Now, because we have two triangles, we can use the concept of similar polygons to find the other sides, but also to find the area of the another triangle. Because on this one it is we can use this one and this one to get the area, but on this one it is a bit difficult because we have on one side and we have on one angle. But we are going to use the concept of similar polygons to work on that. We have to start comparing. Here we have 90 degrees and here we have 90 degrees. But as we discussed that this vertex C, it is common. It is formed by both triangles. It is formed in this triangle, we have vertex C, but also in this triangle, we have also vertex C. So we have to think or to verify whether they are similar or not. First, as I said, we have BAC and AGC. As I said, this angle and this one, they are equal. Why they are equal? They are both 90 degrees. And of course, we are given from the figure, we've been told that they are right angles. Then, and this one, it is common. ACB and DCA, we said it is a common end. Why so? It is formed by both two triangles. Therefore, if you measure, you are going to get the same on the first triangle, but also on the second triangle. It is common. And again, ABC and DAC must be also equal. The reason why it must be equal is that will be the third angles of the triangle. If this and this one are equal, this one and this one are equal, therefore also this one must be equal. Why so? Because we know that each triangle, it has 180 degrees. Therefore, if this one and this one and this one are equal, this one will complete equal to 180 degrees. But we are saying that if we add that this one and this one gives 90 degrees and we are given this one and this one are equal because of the common angle, and this one because of the third angle of the triangles. Therefore, this one and this one are similar. And are similar by using which rule? We actually use the AAA rule. Angle rule. We have used the angle and angle. So what we have used to confirm that they are similar triangles in the what? Angle rule. The corresponding size is 1, it will be equal to 6 centimeter, and S2 it will be equal to 10 centimeter. Yes, this one to be the corresponding size. Let us discuss a bit on how to know that they are corresponding size. What you have to observe, we have to observe the angles. Observing here, the 90 degrees, it is formed at A. And the opposite to angle A is this side, BC. Again, on this triangle, 90 degrees is formed at D, ADC. And the opposite to this one is AC. Therefore, here BC corresponds to AC. This one will be the corresponding side. Similar, this is C, and here this is the C. This one is opposite to this side, AG. And here C, it is opposite to AB. Therefore, AB, it will correspond to AD. So this one will be the corresponding size. And the last one to be this one. Which one? B. Yes, B corresponds to A. A faces AC, while here A, it faces DC. Therefore, this one and this one will be the corresponding size. Therefore, on that one, on finding DC and the AG, you can use the corresponding sizing and the ratio for the corresponding sizing to get that, because we are given one of which is this one and this one. So you can take the ratio of this one and you can use it to find the other sides which are missing on the triangle ADC, since they must have the same ratio. Now, as we said, S1 is 6 and S2 is 10 centimeter. Therefore, finding the ratio of the corresponding sides, it will be this one over this one. Now, working this one, substituting, it will be 6 over 10. Simplifying, you get 3 over 5. That one to be the ratio for the corresponding sides of the given similar triangle. Now, as I said, I'll I'll discuss much on the case of the area of the triangle ADC. So by knowing the ratio of the corresponding sides, we know that the ratio of the area is going to be k squared. So we have to take this one and square it. Squaring there, you get 9 over 25. Now, with that concept, we can use now to relate the area of the triangles. We said we have the dimensions of the size of the triangle BAC, which we can name it A2. This is the bigger triangle, and if we refer to that figure, this one to be the, since here there is a 90 degrees, so this one can be considered the base and this one considered at the height. Therefore, to be a half times 6 times 8, since the area of the triangle says a half times base times height. Therefore, to be a half times 6 times 8, working on this one you get 24 centimeter square, because it is the area, and we know that the units for the area, it must be a square unit. Therefore, it is going to be what? Centimeter square. Let the area of the another triangle, which we are required to find, the triangle area of the triangle ADC, let's name it by A1, sorry, it should be A1. As we say, the ratio of the areas, that is to take A1 over A2, it should be equal to k squared. Since we discussed that, if the ratio of the size of the corresponding size is k, therefore the ratio of the areas is going to be k squared. Therefore, A1 over A2 it should be equal to k squared. But we say the ratio of the size it is 3 over 5. If you square it, you're going to get 9 over 25. Now we have to relate. With this concept, we have to relate A1 over A2, it should be equal to the obtained ratio. The obtained ratio is 9 over 25. So we have to take A1 over 24, it should be equal to 9 over 25. And that one implies that if you apply your cross multiplication, it's going to be 25 times A1, this one and this one. This one to be equal to 24. This 24 we have to multiply by 9, so it's going to be in this way. Now our concern is to find A1. Here A1, you can make it the subject, so it will be 24 times 9 over 25. Working on this one, you get 9.64 centimeter square. That's the area of triangle ADC. This one will be the area of the triangle ADC. So as you can observe, it is very simple. Even on the cases of the side ADC and the DC, you can use the concept of the corresponding size, and there you're going to get the correct answers. Yes, with this example, it marks the end of my lesson, but here I prepared some questions for you, so that you can work, you can integrate the concept we discussed, the way you can apply, but the way it tries to keep the picture, the way it can work in the real life. Thank you so much for your cooperation. Keep visiting us. I invite you to join again the other lessons which are coming later.